Hello, my fellow chemists, and in this video we're going to take a look at scientific notation. Sometimes numbers are not convenient to write the way that they are because they're either extremely large or extremely small. And this happens a lot in the field of chemistry and in science. So today we're going to take a look at if you have one of these really large numbers or really small numbers, how to write them in a much more convenient way so that you lessen the chance of accidentally putting in an extra zero or leaving a zero out. So, a couple examples of numbers that are just very unwieldy the way that they are is if you have one drop of blood and you want to know how many molecules are in that drop of blood, that one drop of blood will have 1, 600, comma 000, comma 000, comma 000, comma 000, comma 000, comma 000 molecules in it. Now, if you have to write that number several times a day, there's a really good chance that you're going to either add in a zero or leave a zero out. Now, another example of a really tiny number is if you want to weigh how much each one of those molecules in that drop of blood weighs, they would weigh 0.00000000000000000000000000003 grams. And again, that's another extremely large or small number. In this case, extremely small. There's a really good chance if you had to write that out multiple times that you'd add in or take out a zero, which would give you an incorrect answer. So when we do scientific notation, it's just a way to write these very large numbers in a much more manageable way. So that top number there, that 1 comma 6 with all the zeros after it, written in scientific notation, would be 1.6 times 10 to the 21. You can see that's much more manageable than that large number. And that second number would be written as 3.0 times 10 to the negative 22. So let's take a look at some examples of numbers and go through how we would convert them from numbers into scientific notation, and then we'll also take a look at scientific notation and how to convert them back into numbers. This video is labeled as basic, green up here, because there's really no background information that you need to know in order to understand the concepts that I go over in this video. So let's take a look at some examples here. So up top, I have some numbers, and I convert those numbers into scientific notation. And the first example is 1 million. Now, that's not a super large number, but for our first example, it'll get the point across. So let's say that we have the number 1 million, and we want to convert that into scientific notation. The first thing that you have to do is you have to realize where the decimal point is in that number, and it's after the last zero, so that's the decimal point there. And then you're going to move the decimal place over so that you have a number that is between the size of 1 and 10. So if we move the decimal place one spot, that's not between the size of 1 and 10. If we move it two spots, we're still not at between the size of 1 and 10. If we move it three spots, still not. If we move it four spots, we're still not. If we move it five spots, we're still not. And if we move it right here, we are. So 1.0. That is at least the size of 1, and it's no bigger than 10. So we're going to move our decimal place over to here, which gives us 1.0 when we do that. Now what you're going to do is write a times symbol and then put a 10. And this just means you're moving the decimal place. And how many positions do you need to move the decimal place? Well, if we look at how many we moved we moved it 1, 2, 3, 4, 5, 6 times. So that's going to be a 6. And then the last question that you need to ask, well, is it going to be a positive 6 that I write up there or a negative 6? If the 6 is positive, that means your number that you have here is going to get bigger. And if it's negative, that means the number that you have here is going to get smaller. Well, 1.0, does that need to get bigger or smaller to get to a million? It needs to get bigger. So that 6 is going to be positive. So to write 1 million in scientific notation, it would be 1.0 times 10 to the 6. Again, the thing that you want to keep in mind is that you want to move the decimal place until you get to a number that is at least the size of 1, but smaller than 10. So between the size of 1 and 10. So that's why we got the 1.0. A common mistake that I have students make that when they do this, they'll say 10 2.0 times 10 to the fifth. Well, that will still get you to a million, but that is not the correct way to write a million in scientific notation because your number out front here is 10 or larger. So you want that number to be between the size of 1 and 10, and that kind of gives you an idea of how far to move the decimal point. So let's take a look at another example of converting a number into scientific notation. So the second example we have here, the number is 0.00237. All right, so now what we're going to do is to convert this number into scientific notation, we're going to again start moving the decimal place until we have a number that's between the size of 1 and 10. So we move it one space, we're still not between the size of 1 and 10. Two spaces, we're not between the size of 1 and 10. If we move the decimal place 3 spots, we have 2.37. That is between the size of 1 and 10. So we're going to write 2.37 and then times 10 to the, that's just telling us we're going to be moving the decimal place. How many spaces did we move the decimal place? Well, 1, 2, 3. So we move the decimal place 3 spaces. Now the only question is it going to be a positive 3 or a negative 3? Well, to get to our starting number that we had up here, this number needs to get smaller. So that means the 3 is going to be negative. So 2.37 times 10 to the negative 3 means I'd have to move the decimal place 3 spots over to make this smaller. So those are two examples where you're starting with numbers and converting it into scientific notation. Now let's take a look at a few examples of scientific notation and how to convert them into numbers. So if we had 3.4 times 10 to the 8th, what you would do is the 8 is positive, so that means this 3.4 needs to get larger. So we're going to move the decimal place 0.4, we're going to move the decimal place 8 spots so that the number gets larger. So that's 1 spot, 2 spots, 3 spots, 4 spots, 5, 6, 7, and 8. And each spot that you moved it, you're just going to add in a 0. There we go. So now we have our zeros, and then we can just kind of rewrite the number down there so we don't have all the wavy lines on it. So it's 3, 4, 0, 0, 0, 0, 0, 0, 0. And that would be, if we put our commas in, that would be 340 million. Now I'm not putting the decimal in here, but there is a decimal all the way at the end there. So we can see we move the decimal place over 8 spots, 1, 2, 3, 4, 5, 6, 7, 8, to go from 3.4 times 10 to the 8th, and that gives us 340 million. And because the 8 was positive, we made that 3.4 larger. We take a look at another example where we go from scientific notation into a number. If we have 3.5 times 10 to the negative 4, now we need to, this negative 4 is telling us that we need to move our decimal place 4 spaces, and we need to make this number smaller. So if we have 3.5 and it needs to get made smaller, then we're going to be moving the decimal place to the left 4 spots. 1, 2, 3, and 4. There's our decimal. Then we just put our zeros in. So that comes out to 0.00035. So if you have 3.5 times 10 to the negative 4th and you convert it into an actual number, it would be 0.00035. So there's a couple examples of converting numbers into scientific notation or scientific notation into numbers. The most important thing that you need to be aware of is, are you going to make this number up here positive? If it's positive or negative, that determines whether it's going to get larger or smaller. If you have a negative number, that means this number you have out in front here has to get smaller. And if it's a positive number, then that means the number that you have out in front has to get bigger. So let's, before we end the video, let's take a look at one example of a problem where using scientific notation would be practical in the problem. So let me just shrink this down a little bit here, and we'll bring the problem over here. So it says, if a piece of dust weighs 890 micrograms, how many kilograms does it weigh? Now, again, this problem does assume that you know how to convert within the metric system. If you don't know how to do that and would like to learn, I'll put a link up in the top of the video there that will take you to how to convert in the metric system using um, the factor label method. But let's kind of take a look at this problem and why using scientific notation to solve this problem would be useful. So if we have 890 micrograms and we want to convert that into kilograms, the first thing we need to do is convert the micrograms into grams. So I'll put a gram down or a microgram down here and a gram up here. So micrograms and micrograms cancels out. Grams is the larger unit, so I'll put that as a 1. And micrograms are 1/millionth the size of a gram. Okay, so now micrograms and micrograms will cancel out. And then we'll multiply across and divide up. And when we do that, we come out with a number of 0.00089. 0.00089. Now that number is not super huge or super small, but it would be much more convenient if we could write that in scientific notation. So that would be, in scientific notation, it would be 8.9 times 10 to the negative 1, 2, 3, 4, because it's going to be getting smaller. 4. So 8.9 times 10 to the negative 4 is the same thing as 0.00089. What units are on that? Grams, because that's the one unit that didn't cancel out. But that's not what the problem is asking for. It asks us to get into kilograms, so we have to do another step. So now if we take that 0.00089 grams, we write another conversion factor for it. Put grams on the bottom so they cancel out. Kilograms on the top because that's what we want to get to. Kilograms is the larger unit. It's the big one, so that's why we put 1 up there. And there are 1,000 grams in every 1 kilogram. Again, we have the problem set up so that grams and grams cancel out. For any factor label problem, we multiply across and then divide up. So if we take 0.00089 times 1, it just gives us 0.00089. But then when we divide that by 1,000, it gives us a huge number, or a super tiny number, 0.0000089. So that has 6 zeros in it. So 1, 2, 3, 4, 5, 6, 8, 9. And the unit on that is kilograms. Now this number is starting to get really small. So this would be much more convenient to write it as a scientific notation, which would be 8.9, because that makes it between the size of 1 and 10, times 10 to the, and then we have to count how much we move the decimal place. So we move it 1, 2, 3, 4, 5, 6, 7. And this number then needs to get smaller, so it would make it a negative 7. So it would be 8.9 times 10 to the negative 7th kilograms. And that's the final answer if we want to convert 890 micrograms into kilograms. And you can see how that final answer is much more convenient to write in scientific notation than with all of those zeros. And when we start looking deeper into the field of chemistry, we're going to see that there's calculations where you get answers that will have 20 zeros behind it or 20 zeros in front of it. So even much larger or smaller than this. So it is very useful to make sure that you understand how to put numbers into scientific notation. Okay, well, that's it for the video. I hope you learned something, and I'll see you in the next video.